In this video, we're going to be solving systems of linear equations using matrices. We've covered the row operations in a different video. This video is where we're going to sort of develop our strategy where we use those row operations together to, to solve a system. So we'll start with a question or a problem. We want to solve the system represented by the matrix, this matrix here. Now remember how these work. That system will be 3x plus 5y equals 9, 1x minus 2y equals negative 8. So it's a system of two equations and two variables. This is what we call our coefficient side, and this is what we call our constant side. So, as we mentioned in the other video, our goal is going to be to get our matrix into a form, the same size, with ones along the principal diagonal, zeros everywhere else, and a column of numbers over on this side. That's what our hope is. If we can get it in that form, then the system does have a solution, a single solution. It might not be possible because some systems don't have solutions or they have infinitely many solutions, but we're going to work towards this goal. And our strategy is going to be to work one column at a time. And while we're working that one column at a time, in that column, we will get the 1, then get the zeros. Now, I'm saying zeros because in a larger system, there will be multiple zeros. In this case, you get the 1 and then you get the 0. Then we'll move to the next column, get this 1, and then get this 0. That's going to be our overall strategy. So let's start by getting the 1 in the position where we need it in this first column. Notice I do have a 1. So the easiest way to get a 1 into that position is to just swap my rows. So row 1 swapped with row 2. Remember, this is the notation that we use for the row operations, and you do always have to show your row operation when you are doing, well, if you're solving it just for your own purposes, you can write things down however you want, but when you're supposed to be communicating your process, you need to communicate your process. And so now row 1 is 1, negative 2, negative 8, and row 2 is 3, 5, 9. They've simply swapped positions. So I have my 1 where I want it. Next, I want to get the 0. I need to change 3 into a 0. Remember, you're not allowed to multiply a row by 0 because that would just wipe it out entirely. What I need to do is add in a negative 3. And the way that I'm going to get that negative 3 is negative 3 times row 1 plus row 2. Let's see why that's going to work. Since I already have a 1 in that position, when I multiply that 1 times negative 3, I'll get negative 3. And when I add that to the 3 that already is here, that'll change. A negative 3 plus 3 is 0. So that's nice. We're going to be storing that in row 2. My pen has turned a little bit blotty for some reason. So row 1 is going to stay exactly the same, so I've just recopied it. Now row 2, I'm going to figure this out by doing one column at a time. So negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times negative 2 is positive 6. Positive 6 plus 5 is 11. Negative 3 times negative 8 is positive 24. And positive 24 plus 9 is positive 33. All right. Notice that that completes that column. This column looks exactly like it does in our goal, so that's nice. Next, we move over to the next column. I want to get the 1 and then get the 0. The 1 needs to be where the 11 is. So this 1 is here. So my 11 needs to change into a 1. The most reliable way to change an 11 into a 1 is to multiply by the reciprocal. Well, the most reliable way to turn anything into a 1 is to multiply by the reciprocal. Notice that what I definitely don't want to do is anything involving adding row 1 to row 2, because that would get rid of my 0 that I already have. I want to keep that. So I'm going to multiply row 2 by 1/11. Multiplying won't change my 0 because anything times 0 is 0. And now row 1's going to stay the same, so I'm just going to recopy it. And row 2, I'm going to multiply everything in row 2 by 1/11. So 0 times 1/11 is 0. 11 times 1/11 is 1. 33 times 1/11 is 3. So there is my 1. Now the only thing left to do to get it to look just like my goal is to change this negative 2 into a 0. So the way that I need to do that is by adding the opposite. So the opposite of a negative 2 is a positive 2. So we're going to take a positive 2 times row 2. Notice that my 1 is in row 2. Then I'm going to add that to row 1, and we'll store that in row 1. So 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus negative 2 is 0. That's the whole reason we chose that. 2 times 3 is 6, plus negative 8 is negative 2. And now I get to just recopy row 2. And there is my final matrix in the reduced row echelon form that I wanted. Now I need to be able to interpret this. Remember that this represents the equation 1x plus 0y equals negative 2. So that tells me x is equal to negative 2. And this row represents the equation 0x plus 1y is equal to 3. So y is equal to 3. We always want to express our solutions to a system of equations as a point. So this is the point, negative 2, 3. Let's do another one. So my instructions are the same. Well, they're not written, but they are the same. I want to solve the system represented by the matrix using our row operation methods. I am going to come off to the side here and rewrite the fact that my goal is to get it in this reduced row echelon form where they have 1s along the principal diagonal, 0s everywhere else on the coefficient side, and then some column of numbers on the constant side. That is what I'm hoping to end up with. So now, well, before I was able to get what I wanted just by swapping. Unfortunately, now I don't have any. I don't have any ones. The easy way to get a 1 when you need it is to multiply by the reciprocal. And I want to point out, if you look ahead a little bit, this isn't going to be bad at all because the reciprocal of 2 is 1/2. And if I multiply everything in this row by 1/2, I'll end up with whole numbers, well, integers, because everything is even. So my first row operation is 1/2 times row 1, and I store that in row 1. So 1/2 times 2 is 1. 1/2 times -4 is -2. And 1/2 times 12 is 6. Then I just recopy row 2. All right, now I need to change this. I just realized I like the numbers 3 and 5. Never mind. Now I need to change this 3 into a 0. Because remember, we work column by column, getting our 1 and then getting our 0. So I'm going to do a -3 times row 1 plus row 2, and I'm going to store that in row 2. So I've just recopied row 1 because that's going to stay the same. Now, -3 times 1 is -3, plus 3 is 0. -3 times -2 is +6, plus 5 is 11. I'm getting a very strong sense of deja vu here. -3 plus +6 is -18 plus 7. Well, -18 plus 7 will be -11. All right, so now my first column is perfect. So I'm going to move on to my second column. I want to get the 1. There needs to be a 1 right where this 11 is. So 1/11 times row 2, store that in row 2. All right, so I'm going to just recopy row 1 because that's not going to change. And then 1/11 times 0 is 0. 1/11 times 11 is 1. And 1/11 times -1/11 is -1. So I've got my 1 where I want it. Now I just need to get this 0. And I'm going to make that a 0 by multiplying 2 times row 2 and then adding that to row 1. I'm choosing a 2 because it is the opposite of -2. So when I add those two together, a 2 and a -2, I will get a 0. So that'll give me a 1. Sorry, I should talk this out. 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus a -2 is 0. 2 times -1 is -2, plus 6 is 4. And then I can just recopy row 2. So I have this in my goal form, and my solution is the point 4, -1. All right, so I think that this next one is more different. That one had a lot of the same numbers, which was totally subconscious. Let's do another one. And again, I'm going to rewrite my goal form over here. My goal is to get ones along the principal diagonal, zeros everywhere else, and a column of numbers on the constant side. So I need to get this 3 to be a 1, which means I want to do 1/3 times row 1, and I store that in row 1. So 1/3 times 3 is 1. 1/3 times -6 is going to be -2. 1/3 times 12 is 4. And I can recopy row 2 because that didn't change. And now I want to change this -2 into a 0. So I'm going to do 2 times row 1 plus row 2, and I'm going to store that in row 2. The reason I'm choosing a 2 is it's the opposite of -2. So it's the same, it has the same absolute value, but it has an opposite sign. That's what I mean by opposite. So I'm going to recopy row 1 because that doesn't change. And 2 times 1 plus -2 is 0. So 2 times -2 is -4 plus 4. Well, that's also 0. 2 times 4 is 8 plus 10 is 18. All right, so my first column does meet my goal form. However, my second column, I need to get this position right here to be a 1. However, well, I can't. I can't multiply by the reciprocal of 0. 1 over 0 is undefined. If I add some multiplier of column 1 some multiple of row 1 to row 2, I'm going to obliterate the 0 that I already got. Once you get your entire coefficient side in a row to be 0, that means that you are not going to be able to achieve this goal. So I want to point out what this equation represents. What equation this row represents. This is 0x plus 0y is equal to 18. That means you've got the equation 0 equals 18. So this is something that is fundamentally false. 0 is not equal to 18. And whenever we have something like that turn up, we have no solution. If you were to graph the equations that these two rows represent, you would find that they come out to be a pair of parallel lines. So this system has no solution. And, well, that's our answer. Sometimes that happens. Sometimes you don't get a solution. So let's do another one. So now I want to I want to write down my goal form. I always want to keep in mind what my goal is. So I'll have 1 along the principal diagonal, zeros everywhere else on the coefficient side, and a row of numbers for the constant side. That is my goal. We just saw an example of where we weren't able to reach that goal and what it meant in that case. Let's see if we can get this one to be in our goal form. So, fortunately, this is kind of nice. They've given us a matrix that has a 1 in the correct position for column 1. So that is nice. Now we just have to get the 0 where the 5 is. So I'll need to do that by adding a -5. So -5 times row 1 plus row 2, and we'll store that in row 2. And so -5 times 1 is -5, plus 5 is 0. -5 times -4 is positive 20, plus -20, well, that's also 0. And -5 times -2 is -10. Oh, negative times positive that I have written here is -10. And -10 plus 10, well, that's also 0. So now I have an equation. Well, I have a row that represents the equation 0x plus 0y equals 0, which 0x, well, 0 times anything is 0, so 0x plus 0y is really just 0 equals 0. Now, this means that that second equation was really just a multiple of the first equation. And if you look at it, you can tell that the second equation is just the first equation multiplied by 5. So here we have a dependent, two dependent equations because they have the same, they have the same graph. If you were to graph these both, you would get the same graph. One is just a multiple of the other. So there are infinitely many solutions here. Every point on the line that is the graph of both of these equations, because they have the same graph, is a solution. Both of these equations can be written. So I'm going to take this over here. So this row is 1x minus 4y equals 2. And the other equation, or the other row, was just a multiple of this. So this is really all we're working with. Every point on this line is a solution. I want to express my infinitely many solutions as a set of points. You read in the textbook last time how to do that. So we can make y be our arbitrary variable and then solve for x in terms of y. For this one, that'll be kind of nice. I add 4y to both sides and I get x equals 4y plus 2. And so this is the form that the homework system will expect your answers in. It will tell you which variable to make arbitrary. I think it will always use y. You can do it with the x arbitrary and y in terms of x, but this is the way that you're going to be expected to do it for the homework. Let's have one final problem. So I've got the same goal as always, and I'm going to write it again. Now, I need to get a 1 in this position, but if I multiply by 1/25th, I'm going to have to deal with some fractions. I don't necessarily want to do that. Or I could swap and then divide by 10. You get nice clean numbers when you divide by 10, but still, it's still dealing with fractions. I want to point out that we said that we were going to work one column at a time. We don't necessarily have to do the first column first. If you're going to do what is called strict Gauss-Jordan elimination, you're supposed to do the columns in order, but we're going to allow ourselves to do a flexible process where I'm going to get my second column perfect first, then I'll do the first column. So I've already got the 1 where I want it. Now I want to get rid of this -3. So I will have 3 times row 2 plus row 1, and I will store that in row 1. So 3 times 10 is 30, plus -25 is 5. 3 times 1 is 3, plus -3 is 0. 3 times 25 is 75, plus -60 is 15. And then I can just recopy the second row. So notice I avoided having to have any fractions. And now, when I get my 1 where I want it for the first column, I won't have to deal with any fractions either. Sometimes it will not be possible to avoid fractions, but when you can, it's sort of nice. So I want to change this 5 into a 1, so I'm multiplying by 1/5, multiplying row 1 by 1/5. So 1/5 times 5 is 1, 1/5 times 0 is 0, and 1/5 times 15 is 3. Then I've got 10, 1, 25 for my second row, and I want to change this 10 into a 0. So I'm going to take -10 times row 1 plus row 2, and I'm going to store that in row 2. I'm recopying row 1 since it's not going to change. And then -10 times 1 is -10, plus 10 is 0. -10 times 0 is 0, plus 1 is 1. -10 times 3 is -30, plus 25 is -5. And so I do have a solution, since I was able to get this in my goal form. I do have a solution, and that solution is 3, -5. And that is our final example of solving linear systems using matrices. Next learning module, we're going to be doing more of the same thing, except we're going to be solving linear systems with 3 variables and 3 equations. So you'll want to get comfortable with this process in these smaller systems so that you're able to tackle the larger systems in the next learning module.